Okay, welcome everyone. Our QCourse 551 first edition. So this will be third collective meetings for Blue projects. I think Sunday midnight I just removed, like exclude inactive students. Currently there are 30 students in Blue projects, but I also I was, let's say, acknowledged that some groups, like only one person make the progress and the others like don't join, etc. Uh, these people will get zero probably from because if they don't contribute for like this collective meetings, we assume that they don't present their progress to us. Uh, So I will check inactive students to blue students, and then I will focus on this. That means even if we have 30 students, maybe it can be a little less. So I try to keep it strict because we don't have like enough time. Also, it's online. Already there have been several technical issues. So yeah, this is a great opportunity. I don't want to repeat again. Uh, and I mean, you should use it. I know that when it comes free, students maybe don't appreciate enough. I really don't understand. I mean, when putting money, why it becomes more like attractable. This is a great opportunity. Try to do your best. This shouldn't be different than your other courses. And I will just exclude one by one. I mean, it's not like, okay, there is no student, etc. Because I see that some people still doing their best. Even we finish 10 students, we will finish with 10 students. Okay, this is a great opportunity. Just please use it. Okay, is there any question or remark, comment for starting? I will ask first 27. They didn't present October 31st. QSynapse, is there any here? If your mic doesn't work, also please write in the chat.
Yeah, it's Mital. Ashmit, QCourse is us actually, so I see you're here.
Hello. Now my mic is working.
Ashmit,
Yeah.
You missed one progress as a group, correct?
Yes, sir.
Okay, you should do it in the future. Not now, but we will ask probably more of this.
Sure, sir.
And if you are ready, I will give the floor to you. Okay, you can share your screen and then start.
Okay, I am getting that host has disabled the screen sharing.
Oh, sorry, it's my fault. You are very right. All participants can share. Okay, now, sorry, it's my fault.
Yep, now my screen visible.
Yes, you can start. The floor is yours. Thank you.
Okay. So my project is about implementing quantum neural network algorithm for classification of MNIST dataset. It is a dataset of handwritten numbers, and we need to classify it using quantum neural network. And I, along with my three teammates, Asif, Saad, and Roman, we are working on this. And so today's agenda will be introduction to QNN and then our problem. I will be sharing about my project milestone and about three steps that we have covered till now. And then I will be sharing next step and challenges. So first of all, quantum neural network. It is basically quantum algorithm based on parameterized circuit for working on problems that are Similar to classical network, hi, yep, I'm sorry, my connection just break. So I was telling about our weekly project milestone. So in the first 3 weeks, we were just discussing our project and prerequisite. In next 2 weeks, we were pre-processing our data and were planning how to process classically shrink our data and encode it into a quantum circuit. This week, we are mainly focusing on designing the quantum layer and other now for in future we will be training and testing our Q&A and then extend our project research. So this is our Q&A architecture that we have decided. We will be first pre-processing our data set. Classically, this involves shrinking our data size. Originally, they are 28 cross 28 pixels. We want them to shrink to at least 4 pixels, but currently we are getting an optimal result on 8 pixels only. So we want to shrink it more. If ideally it's the 4 pixel, 4 by 4 pixel image. And then we quantum for quantum encoding, we are using angle encoding for encoding the pixels of our image into quantum circuit. Then we will be creating quantum layer, and then it will be followed by classical layers for post processing, and then classification. So this is the second step, pre-post processing of our MNIST dataset. Currently, I have used transforms module of PyTorch to just shrink our data images. Initially, they are of 28 pixels. I have shrunk to 8, 8 pixels, but shrinking more than this is causing in a loss of our image data. In this third step, we are encoding our shrinked data using angle encoding. So we are just simply encoding into the angle by of RY gate. Initially, it was taking 1 pixel per qubit, but 1 qubit per pixel. But our mentor suggested that we can do it by like 1 qubit per 2 pixel using 2 gates for encoding 2 pixels in single qubit. So now we will be using one RX and one RY gate per pixel per qubit to encode 2 pixels in an image. Okay, so our future plan is to first create a quantum layer and then optimizer and then polling. The layer will be a parameterized quantum circuit, and then we will be exploring more about stochastic gradient and polling. So the one of the challenges that I am facing is currently that, as I explained, we require currently 32 qubits for encoding single dataset image. That too after shrinking it to 8 pixel, 8 by 8 pixel. So we want to reduce it more, so such that we need 6 to 8 qubits for making it practical. And then we have shortage of computation power. So these are the resources that we are following. So first one is the paper about quantum on chip training, and then we are using classic QNN user guide. And for like project report, this is my project report, which I am maintaining a project blog about our report. I will show it in a second. And this is our code repository for further reference. So yeah, current stage is our for processing and decreasing the qubit requirement for designing the quantum layer. And let me show you the brief report that we are maintaining. So in this report, I am maintaining all the workflow and all the work that we are doing. And this is a long report which you can follow for all the details that we have, step-by-step details that we are following. Yep, finally, I'm open to any questions. Hello.
Ashmit, I think Abu might have dropped off from the meeting for a bit. That's why he isn't responding.
Okay. Okay, my voice was audible all through all the presentation.
Yeah, there was a break, I think, when Abu dropped off. That I think that's what caused an issue on your end as well.
Yeah.
Any questions from the participants?
Yeah, I'm not sure. Has this done before? You never say anyone like state of arts. Is this brand new or someone already done it?
Sorry.
You see something here, right? Has someone else all done same job before? I saw some other documentation already done same job before. So what's the difference from others?
Yeah, I actually discovered while working one of the repository that did the same work using PyTorch and Qiskit. Uh, Currently, our goal is to just first re-implement in Classic this without referring to that code base and that project. We currently our mentors suggested us to first re-implement this using Classic, and then we can add optimization like reducing the number of qubits required and other stuffs. Let me show you the paper that I got to know about, but we are not following that. Yeah.
Okay, so how are you going to use the classical at all? You don't say anything about how to use classical.
Sorry.
How do you? You look at how are you going to use classical to do the job? What do you do? What do you do with classical?
Mm-hmm.
We're going to use
so
classic
we
SDK,
will be
right?
using.
So you're not going. How do
In
you
the
use
next
classic?
step.
Okay.
Yeah. Yeah. In the next step, we will be creating quantum layer using classic QNN module that we will be using for creating classic for quantum layer.
Okay. All right.
That's our next step after deciding the encoding part. Maybe anyone else also like to ask any question?
Oh, have you looked at other methods of PCA? I know you mentioned the degradation of the digits. That's something in quantum to look into, because I've been doing a project on outside on that, and that's something that's really interesting, like PCA in quantum.
Can you just repeat the first line you said?
Oh, so in terms of your high dimensional reduction of data in quantum, it is an active area of research. And it's something I was wondering if you looked into, not just going for the first obvious solution of reducing dimensionality, but there are other methods that people are looking to specifically for quantum, because PCA, like the regular PCA function in like PyTorch, doesn't always give the best results. So I was wondering if you did look into that at all.
Yeah, so we are open for such research, but first our initial plan is to go through a simple plan. So first we will tackle this problem by just the first solution that comes into our mind. Then we will be researching in next phase, that is from week 10 onwards. We will be researching on other methods that are new to us.
Right, thank you, Ashmit. I don't think Abu might be able to join shortly, so we'll still try to continue with the talks without him. The session is being recorded, so he'll be able to review the talks later. Any questions and concerns from your end, Ashmit, about how the group is working?
No, our group is working fine. Earlier in the first week, we were actually it was hard for us to getting started because of lack of communication. But now things are better. Now we are communicating regularly and doing everything together. Now it's fine. But yeah, earlier during the start of war, it was a little bit difficult for us.
Thank you. All right. So next we can move on to Zero, Team Zero.
Sweet. Okay. I'll turn on my camera and share my screen. Cool. There we go. So hi, I'm Crystal, and I'm part of the VZKD or Zero team, and we're working on quantum backtracking. Let me minimize this. And we have a new PI, Eric, who we were able to meet with last Friday. So the first thing I'd like to talk about is Menger's theorem. The theorem says, let U and V be non-adjacent vertices in a graph G. The minimum number of vertices in a UV separating set equals the maximum number of internally disjoint UV paths in G. So this tells us that a graph is K-connected if and only if it contains K-independent paths between any distinct vertices. So our minimum number of vertices tells us something about our maximum number of internally disjoint paths before our vertices are disconnected. So this gives us intuition about how connected our graph is and how many distinct paths there are, which tells us something about our connectivity, the number of partitions or matchings we can make without disconnecting a path. So what we've been doing is looking at the solutions for the game of Sudoku, say using Menger's theorem as represented as a series of paths. So here, for example, in this first square, this is a solved Sudoku puzzle. But in the first square here, we see that we needed 4, 7, 2, and 1 that would represent the completed square. So we inserted 4, 7, 2, and 1, and this would represent steps or states in a random walk. So what we see is that we go to our first node from 4 to 7, and then we go to 2, and then we go to 1. So how is this applicable to our problem? Well, our algorithm has something called marked vertices, which indicates the presence of a solution. And by mapping out our paths, we can find these marked vertices. Knowing the marked vertices and the existence of a solution and applying Grover's search algorithm on these qubits, which we'll call local Grover's search, we can create a speed up in our algorithm. And as a refresher, we had to reread the Grover's search algorithm paper, which tells us that Grover's search originally was about finding a quantum mechanical system that examines simultaneous multiple states. So the original question was based on looking at an unsorted phone dictionary and asking, if we have a directory of n names, how many names do I need to go through before finding a person's phone number? So in the classical case, it would be n over 2 minimum names, but using quantum mechanical systems in a superposition of states, we can simultaneously examine multiple names, giving us only an O square root of n step solution. But the Grover search algorithm usually applies to uniform superposition over all states. And our algorithm is not looking at all states, but at our original marked vertices of solutions, which is a subset of our problem space that I spoke about earlier. So what we've been looking at is using Menger's theorem as a constraint over our vertices, which gives us our number of cuts or independent sets, which we can use for our number of qubits that we need to locally operate over using Grover's search algorithm. So one of the papers that has helped us with this is by Lorenzo and Wikisana, called Programming Quantum Backtracking for Circuit Satisfiability Problem with Divide and Conquer Approach, which is a paper from 2023, so it's pretty recent, that talks about using the root as a state R with T vertices and going from R to T minus 1 vertices to span the tree, where we go from X to Y, where Y is a child of a tree. Because we want to be able to not just span the marked vertex, but every child of a marked vertex and run our Grover search over that, we looked at ways of modeling this via this paper. So in practice, we've been using PyMo, Matplotlib, SymPy, and defining our marked vertex problem as an independent cuts problem using Menger's theorem. And this produces our PyMo constraints. Then we take our modeled backtracking solution states, which we have from our Sudoku solution, and make it into a network X model, which is compatible with classic. Then we generate our constraint for classic using the Menger's cut theorem, which is used to generate our circuits and synthesize our marked vertex qubits using Grover search. So for example, in practice, this is some code that we generated using a solution. This code is by Vanch, and I have circled all the holes physically for the board that our backtracking algorithm found. So these are all the holes, and these are the solutions that the algorithm found. So this would tell us in practice that our solution starts at the qubit assigned to 6, which is this one, and we create a path that represents our state, represented as a tree of 47 total steps. So all of these red circles make 47 steps. So we're still working on a complete solution, but in essence, we define our constraints by an expression. We generate our graph as a Sudoku algorithm backtracking solution that conforms to the network X format. And then we create a PyMo model from the graph input with cuts or partitions and use Grover search to construct our circuit and execute over it. So continuing, we're working on the compatibility of our solution with network X, the marked vertices solution based on a template of max cut and Grover search in classic, which is honestly the most challenging part of the project, which is where we are now. As well as the templates of using templates of the optimization section of classic, which has solutions such as that for the traveling salesman problem and other similar problems. And this is something that was advised by Eric to look at, who's our new PI. And finally, we want to test our solutions for benchmarking and scalability. So for benchmarking, we measure the time difference between our classical and naive quantum algorithmic implementation, which is pretty straightforward. But then we ask, are we measuring the best quantum algorithm in our marked vertex approach? So for Menger's theorem, our results can vary based on the paths that we use. So are we choosing the right one? So to check this, we benchmark this using simulation benchmarking and determine which random walk, as measured by our marked vertex qubit implementation, results in the fastest time and the best performance in classic. And this idea is drawn as inspiration from the paper implementing Grover's algorithm on the IBM quantum computers, in which the authors look at performance as the number of qubits increases for Grover's algorithm. So one possibility is that we can look at larger Sudoku puzzles, since our solutions are tied to the number of qubits that we use. So current Sudoku puzzle is a 9x9, as you saw, and we determine whether our performance of our algorithm degrades as the number of qubits increases. And as we discussed in previous presentations, we intend to submit this work to a conference. And so our next steps include, for that, implementing our marked vertices walk, generating a PyMo model, running the Grover search local algorithm, and benchmarking both classical solutions and the scalability of our algorithm. And if we have time, applying this to some experiments with white box fuzzing, which David will talk about next session. So thank you again. These are references. That's it. And thank you, Eric, who's our new PI.
Thank you very much. What's the size of the circuits you're able to handle right now?
Oh, I don't know that off the top of my hand. I will have off the top of my head. Hold on. I have to grab my collab. So we've implemented a classical solution right now. I have to look for the collab where I have my circuits. A second. I think we had started with like 5 or something. I can't remember off the top of my head.
Okay.
Hold on.
And during the talk, you mentioned local growers. Like, what did the local refer to?
Yeah, so the actual algorithm uses a diffusion operator, which is similar to what you'd expect in, say, Grover search. But it's only operating on the marked vertices. So the way they kind of like in the entire space of the problem, they find a subspace of the problem is by using these marked vertices to eliminate the solutions that would not be, well, the paths that would not lead to a solution then, so an unsat solution. And this is kind of challenging for us. If there's anybody who can help us, because we spoke to Eric, he gave us some of the templates, but really if there's the marked vertex solution implementation is really part of the most challenging section of our project. So if there's a mentor who might be able to also help us with that would be appreciated.
Any questions from other participants?
Yeah, also, so I spoke to the Menger's theorem is actually a conversation I had with my graph theory professor because I'm working with her in a project right now. And she said that's kind of her intuition for something like this, for the marked vertex. But if there's something else, like we're looking at, traveling salesman and max cut and Grover's search max cut. But if there's another type of model that might be, that a PI might be able to see, oh, maybe this is the wrong model for what you're searching for, yeah, hit us up as well. Thanks.
Right. So the one thing that you mentioned when you were comparing with benchmarks, one thing that came to mind is it would be nice to know, like, what are the state-of-the-art classical heuristic approaches for this case, right? Rather than just comparing to naive classical approaches, what would be the state-of-the-art classical approach? So that would be able, you should be able to compare that, hey, here's our optimized quantum version, and this is how it compares to the state-of-the-art heuristic classical approaches.
Oh, that's really good. I saw, so I also, my lab does programming languages, and I did a formal methods summer school. And one of the implementations of Sudoku backtracking that I saw, but we didn't use that one, is using this SAT solver called YICES, YICES. So they kind of offload, outsource the constraint solving part to YICES. Right. And then it returns the list of solutions. So that is something that we could definitely look into.
Right. Exactly. Yeah. Yeah. All right. So that would be good to compare it and can look at it.
Thank you.
All right. Thank you. Thank you very much. All right. So Team 32 said they wanted to go next. So I guess Theory QPE. Do you want to go first, or is it application QPE?
I could go first unless the application group wants to go first. If not, I'll share my screen then.
Right, so Theory QPE sounds good.
Yeah, then I'll start then. So we are from Theory QPE, the three of us, and I'll start the presentation. So basically what I did during these 2 weeks is, firstly, I created a function where I can generate the QPE results from like a 2x2 matrix. So I can just give it any matrix that I want, and it will generate the counts. Yeah, and I also used a H-gate here so that it can take both the eigenvectors. Yeah. After generating the results from the counts from that, we can plot it as this dots over here. And what we're doing right now is we're doing like the post-processing for it, so that so that we can find the actual theta. So in this case, we can plot the probability, we can curve fit the probability function onto the curve. And so this 3-qubit graph, and then you can see that the max point here is also the theta that they estimated, which is about 2.66, which is correct because it is 1/3 times 8. 8 for recording length. With a larger qubit count, this is 7 qubits, we can see that the curve fit is quite decent too. Then afterwards, I also worked on like a more general version. So I wanted to expand it so that when there's more eigenvalues than 1, so in this case, there's two strings over here. So this is the other probability function they'll be using in this case. And the ones that were used here was 1/3 and half. So 4 and 2 point.
Maintenant, recueillir les 150 pour envoyer.
Yes, what?
Faut envoyer en de 60. Oui, oui, mais si tu donnes ton téléphone, tu l'as envoyé 150, ça va passer. C'est ce que j'avais dans le téléphone.
Please keep going. Please keep going. Somebody's not muted.
Oh, yeah. Basically, yeah, it's 2.66 and 4 out of 8, which are what I use for the matrix. And this is a case with more qubits, like 7 qubits, and we can see the curve fit is quite decent as well. This is the pseudocode I used for the curve fitting. So basically, it takes the t, which is the number of qubits, and also the data of y. The y is the bottom axis, and also the data for the probability. So it's this axis over here. I also takes the two max values, which are this value at 3 and this value at 4 over here in this case, because this will give us our initial guesses later. So I first created like a probability function, so it will basically be able to return the probability of y based on the guesses of the a's and the theta's. I also generated 4 initial guesses based on the two max values, so basically 0.5 before and after the two max values. Then I curve fitted based on these initial guesses and using this probability function, using SciPy's curve fit function. This will give us the parameters, 4 different sets of parameters and covariance, and we'll find the parameters with the lowest covariance. We can plot this graph as seen in here and also return the parameters, which will give us the theta. And I'll hand it over to Christian to talk about the Fisher information stuff about it.
Hi, everyone. Can you hear me? Yeah?
Yeah.
Yes.
Oh, okay, so as Simin said, I'm going to speak a little bit about the post-processing mathematical analysis we have started to do this week as well. And it's on Kramer-Rao lower bound. So for post-processing, to estimate the accuracy of the estimation parameter is also an important stuff. So basically, we are going to derive an expression for the Kramer-Rao lower bound by using the theorem that is the relationship between the variance of the estimator with a function that is called Fisher information. Let me see if I can write on the screen. I'm not sure. Yeah, I think so. So as a mathematical analysis, the variance of an estimator that is called theta hat here is lower bounded by a function called Fisher information. In our case, we have a probability density function that is the mathematical one we derive using without any approximation. Please go to the next slide. That is this one. So basically, mathematically speaking, this is the density probability function that is exact and that doesn't use any approach like in some reference making these sort of problems. So what we have started to do this week is to derive an expression for the Fisher information, and we expect to give a discussion according to the lower bounded of the variance for our parameter estimation along this or the next week. So just to show some progress, So basically, we have started to compute this expression here according to the previous theorem. And now we have a long expression that we have to synthesize for discuss the efficient information. Go ahead. So the further work we expect to do is, according to the code shown by Simin, is to generalize the curve fitting for more than two phases. And according to the mathematical analysis, we expect to give a discussion on the feature information to give an appropriate estimator for our approach. And something that I have read about the estimator is that we have to propose an estimator because we have to test that the lower bound find it through the Kramer-Rao bound must to be tested. So I have to read a little bit more about it just to know how to propose the estimator to test the lower bound. And that's all.
Thank you. So is my understanding correct that you already implemented an estimator and now you want to generalize it for multiple phases?
The one that implemented is not the estimator. That's just the usual QPE based on the like a matrix. So we can estimate the eigenvalue. So one step that we want to do is we want to create a like general case, but we also need to do an estimator thing, which maybe Christian can talk more about the estimator.
Yeah, but basically the main problem we have is to elaborate the post-processing for one phase in one phase estimation problem. Basically, if you can go to the math slide, please. That one, yes. Basically, what we have from the literature is that this density probability function has been mathematically approached using different, let's say, windows, square, sync windows, like perhaps Simin showed the past meeting. Yes. Thanks. So the problem, the main contribution of this project, as suggested by our tutor, is that we give an exact mathematical function for this probability distribution. That is the function we show in the last slides. So basically, we have two ways to follow. The first one is on the technical point. I mean the code. That is the what Simin showed. To test for different samples our probability distribution function. And the second step is to analyze our accuracy. So to analyze how good is our estimation, we need to compute the Kramer-Rao bound using our probability function. That is the step we are doing right now.
All right, thank you. Any questions from participants? All right, if not, Team 32, we'll move to application QPE.
Thank you.
Thank you.
Am I audible?
Yes, you are.
Yeah, okay. Just a minute, I'll share my screen. Okay. So are my slides visible?
Yeah, just now they are.
Okay.
They're on full screen. Yeah, go ahead.
It's on full screen, right?
No, it's still in kind of window mode. It's not, but it works. It's good enough.
Okay, fine. So we are from the applications QPE group. So we are working on the applications part of the quantum phase estimation, and a specific application we choose was the option pricing. In the last presentation, we looked at the theoretical implementation of option pricing. How do you implement option pricing using quantum computers? And this week we promised to use classic software development kit to implement option pricing, but most of the time went in understanding the classic SDK and also different functions that are used to implement option pricing. So yeah, so last presentation, theoretical understanding of performing option pricing, and we arrived at a methodology for calculating the expectation of the payoff for an option and for a single asset option contract. And expectation, this particular quantity, I've explained that we use quantum amplitude estimation to calculate this quantity. And this week we mainly focused on this technique of quantum amplitude estimation and tried to use classic SDK to implement this particular algorithm. So a quick review of quantum amplitude estimation. Suppose I have an algorithm A, which acts on this zero state. Let's call it psi. And this is what you get, psi 0n and psi 1n. In terms of Grover's search algorithm, this was called a good state and a bad state respectively. So we are interested in estimating this value of A. So that's the amplitude for this state psi after the algorithm A acts on 0. We use the Grover's operator. This is the stage 1 of amplitude estimation, where we use the Grover's operator, which was used in amplitude amplification in the Grover search problem. So this is the operator A S0 A dagger S psi 0. So S0 reflects the state about the 0 state, and S psi 0 reflects the state psi about the psi 0 state. And the matrix representation of Q turns out to be this thing, where theta is simply square root of sine inverse A. So this can be mathematically derived, but for the sake of this presentation, I've just skipped the mathematical derivation of this form of Q. So basically, this operator Q rotates the state psi by an angle 2 theta towards the psi 0 state. So this comes from the Grover's search problem. But I'm not going to use this operator to amplify any amplitude, but I'm going to this is used for a specific something else. This is used for something else here. So the eigenvalues, so this is a 2 by 2 matrix. So the eigenvalues of this can be found to be e to the power plus 2i theta and e to the power minus i2 theta respectively. And we let the eigenstates be psi plus and psi minus associated with these eigenvalues. And since this Q is a Hermitian operator, its eigenvectors form a complete set. So I can represent any state psi in the basis of psi plus and psi minus. So this is what I have written next. So now when you act Q on this psi, so when Q acts on psi plus, you get e to the power plus I2 theta as the eigenvalue out. And here you get e to the power minus I2 theta out. So what we can see from the previous slide is that I've used the Grover operator to encode the amplitude A in the form of a phase in this particular state Q psi, because theta depends on A. So, sorry, sine square theta was A. So I've encoded my amplitude as a phase using the Grover's operator. So now since I have, now we are interested in calculating this phase theta, so we can use the quantum phase estimation algorithm to evaluate this theta. And once we have this theta, we can implement, calculate A. So that's the idea. So now we use the quantum phase estimation algorithm. So let me denote 2 theta as 2 pi q by 2 to the power m. So because this form is clear, because in the quantum phase estimation algorithm we used this representation, where m represents the estimation register size. Greater the value of m, greater is the precision of theta. So once you have this setup, so you just have to use the QP algorithm on this state psi, with the estimation register being this 0, whatever 0 is mentioned here. So this is actually a register of size m. So it's 0 tensored m. So once you add QP on this, so you will get two possibilities here. So because there are two specific eigenvectors for Q. So Q, if you measure, there are two possibilities. If at all it's Q or it's Q plus 2 power m minus 1. Again, there's a reason why there is plus 2 to the power m minus 1, because these two phases only differ by an angle pi. So there's a one-line calculation as to why you get a plus 2 to the power m minus 1 here. So once you do the measurement on the estimation register, you can either get a Q or this particular Q plus 2 to the power m minus 1. So once you get a Q, you know what's the value of theta and you know the value of A. So this is essentially the quantum amplitude estimation algorithms, and this is the circuit that does it. So this is the algorithm A. This was basically this was basically n Hadamard gates in terms of the Grover search problem. And here it's any algorithm A. And this is the Grover's operator. And I'm doing a controlled, multiple times I'm acting this Grover's operator as a controlled operation because of the QP algorithm, then applying the inverse Fourier transform to get the phases. So this was the theory part which we explored. We also used classic SDK to try and implement this. So this was the state loading function. So we have to load the state psi. So we have randomly, this is just copy pasting the codes from classic SDK and doing some small manipulations. This is the state we created with these probabilities. So I think I should have, okay. So this is the state we created. It's a 3-qubit state with these probabilities for each state. So there are 8 possibilities, 8 possible states that a 3-qubit can, take. So these are the probabilities which go. So this is what we asked Classic to synthesize, and we got it simulated exactly accurate results, so approximately good results. And once we know how to load a state, now we have to define the other functions, the Grover operator. Basically the Grover operator has 3 different functions. One is the state loading function A, and it also has S psi 0, reflection about psi 0, and reflection about the 0 state. So this is the good state oracle. So basically reflection about psi 0. This is the code for it. So this is the 0 oracle function. Sorry. Yeah, this is the good state oracle function, reflection about psi 0. And this is the 0 oracle function, reflection about the 0 state. And once we have S psi 0, S, and also A, which was a state loading function, we put them together using, there is a technique in the classic SDK where they define a composite functions using this, using other simple functions. So the Grover function is a composite function containing these 3 functions. So I put them together, and once you have this, you can directly run the quantum phase estimation algorithm on it. So I forgot to, show the results here. Yeah, that got missed. So this is basically what we did. We basically explored classic SDK to do quantum amplitude estimation.
Could you just mention what kind of results you got?
No. You mean the quantum amplitude estimation results?
Yes.
No, because these are just learning kind of codes. So we have the necessary ingredients. Now we just have to use it for our specific project.
But like when you ran this code in test cases,
of course. This this opened a circuit, and I've executed it, and it gave me specific results which I forgot to add it here. That's what I said.
Sure. Okay.
Yeah, but yeah, this yeah.
And what's the project plan moving forward?
So the project plan is to do option pricing using classic SDK. So we have for the past 2 weeks we have learned how to use classic SDK, and also now we have the necessary ingredient setup. Like we know how to do quantum amplitude estimation, quantum phase estimation using classic SDK. Now we just have to specifically do option pricing.
Okay. Any questions from participants? All right, thank you. We'll move to, I guess, team 21. Bill, are you around? No, I don't see Bill. Anyone from Team 21? No, in that case, 26, designing interactive introduction to quantum.
Yes, hello.
Yeah.
26.
Hi,
We
Alvaro.
are yes, hello. We are the education A.
Educators, right?
Group.
Okay.
Educators, yes. Well, I share my screen.
Yes, please.
Can you see?
Not right
It's
now.
okay.
No, I
No?
see camera. I don't see the shade screen.
Sure. Can you see my screen now or not?
No, not yet.
Oh, what a problem. I will stop and share again. Oh, no.
No, we don't see the screen
Host
yet.
disabled participant screen sharing.
Okay, let me change the setting.
Can you see my screen? Can you see my screen now?
No, I still just see your camera.
Share.
Yeah, now we can. I think now it started sharing.
Yes.
Yeah, so we can see your browser right now.
Okay.
Yeah, we got it now.
Yeah. Okay. Thank you. Well, this is the third presentation. We will include in the course videos and interactive presentations. We talked about this last meeting. We will use a methodology of referring in the course the classic documentation to becoming familiar to the student with the documentation. We will not use another tools in the course, only the classic platform, so the student can learn the algorithms, but domain master the platform also. So these are the notebooks, the new books that I will show here. The part of state preparation is completed. All the built-in algorithms of the platforms are covered here. Computational states, this was the last week, Bell states, GAC states, W states. In each case, we go step to step, showing the circuits and guiding to the student to perform the interaction with the platform. Uniform distribution, exponential distribution. This notebook is about errors, about the construction of a distribution with probabilities or amplitudes, and setting the level of error admitted. So we refer here to the classic documentation, as I said, to become familiar to the student with the platform, with the documentation. Then Gaussian mixture is covered here also, and this is the last, the quantum Fourier transform. This is very interesting because the idea is not to explain first the theory, initially explore the quantum Fourier transform with the classic platform. Instead of going to the numeric calculations, the idea here is to test with the platform what circuit, which circuit is generated. So we'll start with a circuit with 1 qubit, and we see a Hadamard. We and so we explain that yes, it is okay. A QFT, a quantum Fourier transform with 1 qubit, is a Hadamard. With 2 qubits, we see the new circuit generated. So we see the output, and we add 3 qubits, 4 qubits, and 5 qubits. So then, when we show to the student the mechanism, the circuit that is generated by the platform, we go to the explanations of the numbers and citating, referring to the Q-work, Q-silver course, as you said in the meeting last time. Here we show that we saw in the platform is the same that the QFT represents according to the theory. Now we develop a question: what does QFT do with, which is the action? And now we explain how to include a state preparation before running the quantum Fourier transform, and show what happened when we prepare a periodic function as the initial state. So we show here the circuit with the state preparation block, and we show the output. So we test with another situation more here, and we conclude that the Fourier transform is a frequency domain representation of the original input. I think that the interesting of this is how the student can play, can interact with the platform before going to the to study the theory, and then when they study the theory, is positioned with an idea about the algorithm, about what he is going to find. Okay, and finally we include a creation of a QFT model with Python, more detailed to see the counts, the form the way to define the transformations, the rotations. Okay, so the next steps are include, as we said, interactive videos, develop an introduction to quantum computing, and the three algorithms that Grover, Simon, and quantum phase estimation that are under developed. We are developing, and that's all. Thank you.
Thank you. Is there a plan to also develop assessments around each of these topics?
Assessment? No, we don't have developed that. We will think how to do it.
Or maybe even just like exercise questions for, as you mentioned, that the content allows students to interactively understand or learn. So maybe have some exercise questions.
Yes. Yes, we should develop some kind of exercise. Yes. Yes.
Okay.
We will do it. Thank you.
Thank you. That's good. Thank you.
Yeah.
All right.
This is, I have a problem to stop the share.
Okay.
Sharing of the platform. Stop share.
Okay.
Okay.
All right. Thank you. All right. Yeah. Team 26. Second team.
Yeah, we are second team, and I will be presenting, so I will share my screen.
Thank you. Your minds, right?
Yeah, entangled.
Okay.
Is my screen visible?
Yes, it is.
Okay. Yeah. So hi everyone. We are second team for Introduction to Quantum Computing with Classic course, and this week, last 2 weeks, we mainly worked on notebooks related to quantum computing, basics of quantum computing and quantum mechanics. So in quantum mechanics, we gave brief introduction, and we covered linear algebra, where we covered scalars, vectors, and matrices and matrix operations, and we also covered complex number and why we need them, and we also covered complexity theory with sample Python examples, and in theory part we also covered basics of quantum mechanics like superposition, entanglement, and what are qubits, gates, and state preparation like Bell state. In quantum algorithms, right now we only covered this Deutsch's algorithm. We have planned to cover Simon's source and Grover's algorithm that we will be adding in upcoming weeks, and then we covered introductory part for classic web IDE and SDK. So for first we gave introduction regarding what is classic and what are its features, and then with screenshots, and we explored how well state is created, and how instead of going at circuit by circuit level, we just need to call the function and specify that function, and classic take care of that. Similar thing we did in Python SDK. So there we showed how to install the SDK, and then how to prepare the state, value state, and execute it using Python SDK. So yeah, that's all we covered till now. our plan is to add quizzes at the end of slide notebooks, and also make videos once our notebooks are complete. And upcoming weeks we will try to cover remaining algorithms and state preparation. We will try to cover more on classic platform specifically. So yeah, thanks.
So where was the text that you're using in the explanation of Deutsche algorithm coming from? Where's the content coming from? Are you generating it yourself?
Yeah.
So if you go
Yes.
to, yeah. So the entire content has been generated from
This
yourself.
part, yeah. Since I had created, so yeah, this parts we are writing manually.
No, I was mentioning Deutsch's algorithm and
yeah.
So the explanation that you're providing over here has been generated by yourself.
Yeah.
Okay. And the IDE material classic overview, isn't that already something that's available for the classic SDK?
Yeah, it is available, but I think it's available for normal state preparation. We covered for but yeah, it's kind of available, but we thought that it's good to include in course.
And what's the content that you plan to include? What's the scope of the content that you plan to include moving forward?
Yeah. So we initially planned to cover basics of quantum mechanics and quantum computing, all theory part, and then basics of classic and state preparation. Then we will also cover Grover search, and at the end we thought that we will include some kind of project, but that we are still not confirmed what we will add.
How many people are working with you?
We were 5 people, and last week we were 4. I guess I'm not sure, but from next week we will be 3 people.
Okay. So I think some of the, I don't think there's enough content in the project to warrant a group of, let's say, size 3 or size 4. So I do think you need to develop the scope of the project a bit more in terms of the amount that you've contributed already versus the amount that should be there in a complete project.
Okay.
Okay. All right. Thank you.
Yeah. Thanks.
Okay. Let's see again whether someone from Team 21 is here now. So it's integration of Metic with Classic. Anyone's here? So there's Bill and Tuba. I don't see either of them here. And I guess that's pretty much it for today then, if they're not here. Thank you, everyone. Most of the talks were great. Sorry about the mess up with the Zoom sessions today. Hopefully it will not happen again. Any questions before we close our session for today? No? All right, then. Thank you, everyone. I'll close the session for today. And we'll see you in 2 weeks.
Yeah. Thanks. Bye.
Thank you. Bye. Bye. Thank you.
Thank you. Bye-bye.
Bye.
Bye.